So the question is what can we do to restore function in spinal cord injury? And so in 2003, I met Suzanne Poon. And at that time, I couldn't believe that she was the mother of a 18, 19-year-old man at that time. and she asked if there was any treatment for her son. And I said no, but I asked her to join me in a partnership to form a spinal cord injury network in China. And we started in 2004, and we launched the China Spinal Cord Injury Network in 2005. Now, in 2006, after we trained all the centers to do clinical trials, we had to choose a therapy to test in the network. And what I want to do is to tell you about the therapy we did choose and what we hope to do with it. So it turned out that the therapy that we chose to test as the first therapy for the China Spinal Cord Injury Network was umbilical cord blood cells and lithium. Many people say this is Wise Young's therapy. I assure you it's not Wise Young's therapy. I didn't know anything about umbilical cord blood or lithium when I started all this. I simply looked at all the candidates for therapies and decided that this was the most promising and the safest to carry out in a clinical trial. So first, I want to show you some pictures of rat spinal cord so you get an idea of what the spinal cord injury looks like. This is pictures of the rat spinal cord that's been had a laminectomy done, and that's the top picture. And you can see the spinal cord is present there. And then a spinal cord that's been injured with a 10-gram weight dropped 12.5 millimeters onto the spinal cord. And you can see that there's some damage to the spinal cord. And then a spinal cord that's been damaged with a 25 millimeter weight drop. Now, 10 grams is very small weight. That's, in fact, my pen is heavier than 10 grams. So it is like dropping a weight this distance onto the spinal cord. And in the middle case, where you can see at the 12.5 millimeter weight drop, you can see that there's still some axons still running through. There's still a little bit of red. There's, of course, an area of severe injury. 90% of rats walk with that kind of lesion. This is the equivalent of an incomplete spinal cord injury. And by the way, a lot of people think incomplete spinal cord injury, you have a lot of axons. It's not true. Most people with incomplete spinal cord injuries have very few axons, probably no more than 15, 20% of their axons. But an animal with a contusion injury of the middle area, these rats all will recover walking, BBB scores of 12, 13, 14. But the animal that gets injured with a 10-gram weight drop, 25 millimeters, where there are relatively few axons running across, these are all paralyzed. They may be able to move their legs a little bit, but they're not able to support their weight, and they're not able to walk. And this is a picture of a spinal cord that's I think this was 16 weeks after injury. And this illustrates what really most people's spinal cords look like after spinal cord injury. You see there's an area of, there's sort of an hourglass-shaped, there's atrophy around the injury site, and you can see that there's a loose matrix of tissue inside the injury site. And we were actually quite surprised to find that out in 1995 when I led a group of 8 leading spinal cord injury centers to do studies on contusion injury. And we found that 70% of the spinal cord that were injured in this way have a loose matrix of tissue, cells at the injury site, and many axons are growing into this matrix, but they don't seem to be growing out. So how would one address that kind of injury, and what should we be doing in terms of therapy? So to an axon that's trying to grow back from its injury point to the original destination, the first area it has to cross over is the injury site. This injury site is bereft of all the signals that normally tell axons to go here or go there. This injury site is filled with, oftentimes with macrophages early on, and then later on with astrocytes. And what we found when we injected cells into the spinal cord was that if you inject cells right into the middle of the spinal cord, generally you get an island of cells and it's surrounded by all this tissue that's not spinal cord, and actually is isolated from the surrounding tissue. So we began to inject the cells in the surrounding spinal cord. And when we did that, we found out that the cells that we inject will actually easily migrate into the injury site and form a bridge. And here I show sort of a graphic depiction of how the way that we think that the cells should be injected. As it turns out, the best way to inject the cells into the spinal cord is at a 45-degree angle right into the dorsal root entry zone. This way, you completely avoid any white matter tracts in the spinal cord. You don't damage anything. All you do is you damage the lesion area just above and below the injuries, the dorsal root entry zone, just above and below the injury site. And we find that in almost all cases, the axons, the cells will migrate into the injury site and form a bridge. And I want to show you some pictures of that. Now, the next question that came up was, what cells should we use? And at that time, in 2006, there were only two GMP sources of cells. One was bone marrow, the other was umbilical cord blood. Now, what is GMP? GMP means good manufacturing practice. This means that the cells are being manufactured by a company or an organization that knows exactly how the cells were manufactured, that document every aspect of it so it is safe. GMP is the industry standard that should be applied to all cells. You know, I worry a lot about people going overseas and getting cells transplanted in India, China, or Caribbean. You don't know where these cells have been. You don't know how they've grown them. You don't know what reagents that they used. And they're putting this into your spinal cord. Not a good thing. You should ask for GMP source cells. So at that time, there were only two GMP sources of cells. One was umbilical cord blood, the other was bone marrow. In terms of fetal cells, of course, many people have been transplanting fetal cells of all types into the spinal cord, but when we looked carefully, we found that there were not enough fetal tissues to allow us to do a large-scale clinical trial, even in China. For example, if we wanted to find 400 aborted fetuses in China, we would not have been able to get them. And then finally, embryonic stem cells, you will hear about them, but certainly in 2006, they were not available. Jaren has started clinical trials with the first embryonic stem cell lines, and so this is, of course, being done now, and I think it's really important. So the first thing we did was we said, well, are umbilical cord blood cells well accepted by the spinal cord? And so we took some umbilical cord blood cells, isolated them, mononuclear cells, injected them into the spinal cord, and I saw two things that really made me feel very favorably inclined towards umbilical cord blood cells. First, these cells don't migrate anywhere. I feel uncomfortable injecting cells into the spinal cord and then a week later finding them in the brainstem or the brain. I like cells to remain where they are, just like little children. You put them down, they don't wander all over the place. It makes me feel more comfortable. The second, which really impressed me, was that umbilical cord blood cells do not evoke a gliosis around them, that there's no astrocytosis. In other words, the glial cells recognize these cells as if they're part of the central nervous system and they are not reacting to them, which is good. So at that same time, in 2004, Wu Tian Wu, who's a wonderful spinal cord injury researcher at Hong Kong University, and he's become a very close friend. Wu reported in a paper published in the Journal of Neurotrauma in 2004 that lithium strongly stimulates axons to regenerate in the spinal cord. I said, lithium? What is this? Lithium is something used for manic depression. By the way, lithium is the most incredible, it's by far the cheapest drug in the world. By the way, I mean, we all have lithium in our batteries. This is the same lithium. It has been used for over 100 years to treat manic depression, has a very, very well-established safety profile. And I said, lithium regenerates the spinal cord? How is this possible? Well, it turns out that lithium inhibits an enzyme called glycogen synthetase kinase 3-beta, and they increase nuclear factors called NFAT and beta-catenin to stimulate cell growth and differentiation. And this has been reported and confirmed by literally hundreds of laboratories. And so we applied lithium to the umbilical cord blood cells to see what they did. What we did was we injected green umbilical cord blood cell mononuclear cells into the spinal cord around the injury site, and we treated the animals with lithium by injecting the lithium into the skin subcutaneously, and we compared this against saline injections, and we found out that when you inject lithium to the animals, that 2 weeks later you see many, many more cells, and these are shown by the green on the two sides of the spinal cord. If you inject saline, you can barely see the cells. Then if you look at the injury site, you see the cells have migrated to the injury site and have filled up all the available spaces. And finally, we went and measured neurotrophins in the spinal cord, and particularly the expression of neurotrophin 3, glial-derived neurotrophic factor, that's GDNF, and then nerve growth factor. And it significantly increased all these three major neurotrophins that are known to stimulate regeneration. So we were actually quite impressed by the fact that we can put these cells in, that lithium not only enhanced the survival and proliferation of the cells, but it caused these cells to produce growth factors that stimulates regeneration. So I want to briefly go over a couple of papers that have been published between 2003 and now that report the beneficial effects of umbilical cord blood cells and lithium on animal spinal cord injury models. Since 2003, over a dozen laboratories have now reported beneficial effects of umbilical cord blood cells transplanted as late as 1 week after spinal cord injury. And I list them here. These are the laboratories. Many of these laboratories have published 5 or more studies. This is one of the first and the most impressive study that was published in 2007 by Dasari at the University of Illinois. And you can see 3 graphs on here. If you look at the graph on the upper left-hand corner, these are the BBB scores. BBB scores were developed by Basil Beatty and Bresnahan. These are walking scores for rats. 21 is a rat that's able to walk normally. 0 is a rat that is unable to walk. A score of 10 is a rat that's able to stand but not walk. So if you have scores greater than 10, that means the animal's able to walk. If scores less than 10, animal's not able to walk. And you can see that there's a separation of the 3 bars, the 3 graphs, or the 3 lines, one of which is cyclosporin treated, one of which is human umbilical cord blood cell treated, and one of which is just simply injured. And the one that's human umbilical cord blood cell treated split off from the other 2 lines. And you can see that those rats actually achieved walking scores of 15 or higher, whereas all the other rats, the control rats, were around 10. So this is a remarkable improvement in walking. That is an animal that's able to stand and not walk to an animal that's able to walk pretty normally, almost normally. And to an untrained eye, this would look like a very good walking rat. But Dasari did 2 additional tests in these animals. First, he made the animals walk on a narrow wooden beam. Now, a wooden beam, a normal rat just would scamper over a wooden beam with no trouble. But a spinal injured rat, because they can't tell where their hind feet are, their legs would slip off the edges of the narrow beam. And so they would put some food at the end of the beam, they have the animals walk. Well, what happens is that The animals that were injured would lose their ability to know where their feet are, and their hind legs keep on slipping off the edge of the beam as they're walking. But those that were treated with human umbilical cord blood cells actually recovered significantly from the other ones. And then the third test that he did was a test that we had developed in our lab. It was really a very nice test. You hold the rat underneath the arm, and so the legs are dangling. And then you put a brush, and you brush each leg, and every time you brush, the legs will go like this. And so it turned out that this test showed very substantial walking. I have 1 minute left, so I'm going to talk very, very quickly here. I just want to show you one study from Lithium, and this is the study from Wu. So if you look at the left-hand side and you see the bars that's going straight up, on the far left, our animals are treated without lithium, and then the second bar is animals treated with lithium, and third bar is animals treated with a drug called chondroitinase ABC, and the fourth bar is chondroitinase ABC plus lithium. A lot of people don't take the time to look at this paper, but with the chondroitinase plus lithium group had 40% regeneration of the cerebrospinal tract. You know, a lot of people talk about 10, 20% regeneration. This treatment regenerated 40% of a tract. This is something to write home to mom about. This is, you know, a lot of people were saying, well, 10% is so great. And Wu also showed that it stimulates stem cells, lithium stimulates stem cells in the spinal cord. So finally, I'm just going to end here. We started the China Spinal Cord Injury Network. These are pictures of the people there. I'm going to go through. We're doing the clinical trials in China, and we finished the CN 100, 101, 102. We're now currently doing 102B, and finally, as soon as 102B is finished, we will start out with a phase 3 study, which will be CN 103. We have now started a USA network, and that USA network will do the phase 3 study in the United States, and we're, as I indicated, we're also doing this in India. This young woman here is the main reason why I started organizing clinical trials in China, because when she left the United States, she asked how would therapies get from US to China, and I said clinical trials, and so I started clinical trials in China. But 3 years ago, when I announced that we're doing China SCI Net, all these Americans wanted to go to China, and I thought this was just not acceptable, that we need to do the clinical trials in the US. So we have now started the SCI Net USA. And so here's a picture of Suzanne Poon amongst all these other guys. And she is the heart and soul of our network in China. The network and all the clinical trials are essentially funded by fundraisers in Hong Kong. So I would be glad to answer any questions, and thank you for letting me go over time.
Visit u2fp.org for more coverage from Working to Walk and the latest in spinal cord injury news.